Hello, I'm Anirudh Shankar Raj. This is my nonlinear controls final project on the topic SE-3, that is special Euclidean group in 3 dimensions, geometric tracking control for a Parrot Mambo mini drone implemented in Simulink and hardware. Trajectory tracking can demand large attitude changes. A PID controller typically uses Euler angles and local linearization, which can fail in aggressive maneuvers and near pitch angles of plus or minus 90 degrees due to gimbal lock. Geometric control works directly on SO3, that is special orthogonal, and SE3, that is special Euclidean groups in 3 dimensions. So it avoids attitude singularities. I run a Mambo quadcopter flight simulation in Simulink and compare a PID baseline against an SE3 geometric controller on hover, circular tracking, and aggressive maneuvers. Then I have verified the implemented SE3 geometric controller in hardware for hover and circular tracking. The mission layer outputs reference signals: position, velocity, acceleration, and yaw. I also include a vision hook for target following, which is an optical flow, and a vision based position signal can update the references when enabled. The controller uses two loop geometric structure. The outer loop forms a desired force or acceleration vector A from tracking errors, gravity, and feed forward. Then A maps to thrust and a desired attitude using normalized vectors and cross products. The inner loop tracks the attitude and the output body moments using P and D terms plus integral action. The base loop runs at 200 Hz with a 5 millisecond sample time, and vision updates run at 5 Hz. The model uses a 63-gram quad rotor that includes a 5 Hz notch filter and a mixer matrix to convert rotor thrust into moments. Next, I'll summarize the tracking results. I evaluate hover and circular trajectories to test both small angle behavior and the sustained tilt required for centripetal acceleration. In hover, PID and geometric control are similar with RMSE around zero point 0.2 meters and attitude excursions near 5 degrees. In circular tracking, geometric control performs better, about 15% lower RMSE and about 57% faster settling time. The larger sustained tilt is expected for a circular motion. In an aggressive figure 8, geometric control converges and settles in about 3.21 seconds while PID continues oscillating. In a high pitch test, geometric control remains stable across the attitude envelope and achieves about 5.6x lower error. PID degrades due to gimbal lock. PID's Euler angle linearization limits its usable attitude range, roughly within plus or minus 45 degrees, and performance can collapse as maneuvers become aggressive. The SE3 geometric controller is singularity free and tracks complex trajectories more reliably with strong stability properties. Next, we will see some experimentation video results that I have captured of both hardware and simulation for hover trajectory tracking and circular trajectory tracking. This is the real hardware video versus the simulation and its results for hovering tracking control. This is the hardware versus the simulation video with the results for a circular tracking control. So, to conclude the presentation, overall, the Simulink SE3 geometric controller improves tracking and stability over PID especially in aggressive or near singular conditions. Next steps are better vision based target mapping, explicit actuator saturation handling, and stronger robustness to noise and disturbances. So, this concludes the video, and thank you for watching it.